All right, so here's written problem 4 where we're doing a fundamental theorem of calculus question. What we're asked to do is determine the derivative of this function g of x, which is defined as an integral of some other function. And so informally, the derivative and the integral cancel, and we're left with almost what you see right here. However, when the bounds are anything other than just the letter x, and that letter is not in this top position, there's a couple little adjustments we need to make. So namely, because this x to the 10th is down on the bottom, we're going to negate this whole thing. And then when we change all of the t's into x to the 10th power, we're not going to be done. We're going to have to multiply by the derivative of x to the 10th. What I'm saying is the answer should be, I'm going to copy exactly what I see here, except everywhere I see the letter t, I'm going to change it to x to the 10th power. And then I'm going to realize that I'm not quite done. I need to negate this entire thing because the x to the 10th is down on the bottom. And then I need to multiply this entire thing by the derivative of x to the 10th power, which is 10x to the 9th power. I'm going to simplify this a little bit. I could take the negative and apply it to each of these three terms. Now this is negative, this is positive, this is positive. I could take this x to the 9th and cancel it with most of this x to the 10th. So I'd be left with just an x down on the bottom. And then I could take this 10 and distribute it to all these terms. I think when the dust settles, I'd be left with negative 10 over x from this first term, and then positive 10x to the 9th from this second term, because you can kind of see this is just 1 right here. And then from this third term, if you think about this as x to the 20th and you cancel 10 of them with this x to the 10th, I get x to the 10th times 10x to the 9th. I get 10x to the 19th, and it's going to be positive because this negative and this negative make a positive. You don't need to do any of this work, but maybe that'll serve as a nice little check when I go through and actually figure out g prime of x. It's worth pointing out that I asked you to do this two different ways. First, by actually determining the antiderivative of 1 minus t squared over t. And you're like, oh, that's really hard. I don't know how to do that. I think you do. We just need to rewrite this in a form that's more conducive. So for this first method here, maybe we'll first rewrite g of x and say that it's the integral from x to the 10th power up to 3 of, let's see, instead of 1 minus t squared over t, I can make this 1 over t minus 1 minus t, by canceling this t with each of these three terms, I guess is how I could describe my work there. And now I believe I can take an antiderivative. The antiderivative of 1 over t is the natural log of the absolute value of t. The antiderivative of this negative 1 is just negative t, the variable that I have. And the antiderivative of this negative t is negative 1/2 t squared. And that needs to be evaluated from x to the 10th power up to 3. And this evaluation isn't too bad. I'm just going to change all the t's into x to the 10th first. And this evaluation isn't too bad. I'm first going to change all the t's into 3's. There's my unnecessary parentheses around the outside. And then I'm going to change all the t's into x to the 10th power. And that gets me here, which I'm going to clean up a little bit. I'm not going to bother cleaning this term up much because I know I'm just going to take the derivative in the next step. And when I take the derivative of this constant, it's just going to be 0. And I guess I couldn't help myself. I cleaned that up a tiny bit. But for this term, maybe I'll distribute the negative through, and I'll call this x to the 20th power. So I got negative natural log of the absolute value of x to the 10th plus x to the 10th power plus 1/2 x to the 20th power. I now have a better form of this function g of x written right here. And when I say better, I mean easier to take the derivative of. G prime of x, the derivative of this thing, well, this is all just some number. I don't know what number it is. I don't care what number it is. So its derivative is just 0. The derivative of negative will stick around. Natural log of x to the 10th. Think chain rule here. You have 1 over that x to the 10th power, but then you're not done. You have to multiply that by 10x to the 9th power. The derivative of x to the 10th power, again, 10x to the 9th power. And the derivative of 1/2 x to the 20th, well, if I bring the 20 down in front, 1/2 times 20 gives me 10. And then I have x to the 19th power. And I believe this is equivalent to what's written here. It's a little bit hard to see right now, but let's see. I have x to the 9th and x to the 10th, so I can cancel out all but one of these x's and put the 10 up on top, and I'm left with negative 10 over x. And then the other two terms are just fine the way they're written. And now it matches what my answer should be perfectly, so maybe I can call that good. Now I'll do this thing again, but with kind of a trick that sort of feels like cheating to me sometimes. This trick involves substitution, so I'll pick whatever my favorite letter is. I don't know that that's really my favorite letter. I'll pick some letter to represent this function inside the integral. It's called the integrand. So f of t I'll let be 1 minus t squared over t. And if I do this little substitution, then g of x is just the integral from x to the 10th up to 3 of this function f of t. And the advantage of running it this way is now it's a little bit easier to apply the evaluation theorem, because the antiderivative f of t, I don't have to worry about what it actually is. I'm just going to use a capital F to represent it. So I would say capital F of t evaluated from x to the 10th power up to 3. And evaluating capital F of t is a little bit easier than evaluating this mess. I could just say, well, if I change all the t's into 3's, I get capital F of 3. And if I change all the t's into x to the 10th, I get capital F of x to the 10th power. And I'm now at the step where I can figure out the derivative of my function g of x. G of x is this thing, so it's derivative. Well, let's see. This is just some constant. I don't know what the constant is. That's a bit of a lie I do because I did it over here. But it's some constant. When you take the derivative of any constant, you just get 0. And then the derivative of capital F of x to the 10th power, well, chain rule. The derivative of capital F of anything is little f of that thing, x to the 10th power. But then I'm not done. I get 10x to the 9th power, the derivative of this inside function, again, necessary because I'm using the chain rule here. And you're like, oh, okay, so what's that? Well, remember, little f of t is 1 minus t squared over t. So little f of x to the 10th power would just be this, changing all the t's into x to the 10th. So I got 1 minus x to the 10th minus x to the 10th squared divided by x to the 10th. And then I have to multiply that by 10x to the 9th power. And at this stage, this might look kind of familiar. I think what's written here is identical to what's written here. So the same logic that turned this into this allows me to turn this into this. And it matches up, hopefully. So I can call this good and be done with this problem.